Okay, hello everybody, good morning. So, do you have any question about previous topics and previous course? Is everything clear? Okay, good. So, today we will have new topic, transfer learning in machine learning. Our course today will have two sections again, but most importantly, there will be time for you that you can practice the implementation and you can practice today's course especially to make sure that you're learning how to implement, because whatever you're studying as the slides, after 2 months, 3 months, you're gonna forget all of them. Because of that, you must make sure that you're practicing writing codes and developing so that you're understanding what is happening. Even if you understand the course completely, if you cannot use it, if you cannot implement it, it's not useful. It's just like you know some theory that is in the shell. So due to that, must make sure that you can solve practical problems with whatever you're learning in machine learning. So today's course is transfer learning. We want to see how we can use same model, the trained model, in order to boost the performance, boost the learning rate, boost the efficiency of the learning based on different problems that we may have. So if you want to have a look at the outline of today's course, we first define what is the transfer learning. Second, we answer why and when to use transfer learning. So we should determine it first. Then we introduce different types of transfer learning, inductive transfer learning, transductive transfer learning, and unsupervised transfer learning are three most common ways to do this. Then we talk about relationship between deep learning and transfer learning. What is the relationship and how we should understand the connections. The concept is quite simple. I quickly will introduce the VGG and ResNet structure because we need to know at least some well-known structures of the deep neural network, so that we can apply and we understand when we want to say, okay, we want to load the weights of the network and retrain from some certain point, continue the training from some certain point. What does it mean? Then I introduce the self-supervised learning, what is the definition and when we can use it. And finally, we talk about recent advances of the transfer learning. So in this chapter, after we study this, all this, you're supposed to know the general concept of transfer learning, how we can bring it to practice. After all this, I will show you some implementations and codes, and you will see what do we mean when we are talking about transfer learning, one of the approaches. So any question? All right. Let's start with definition of what is the transfer learning. We say we want to train a deep learning model from scratch. If we want to do that, it requires a large amount of labeled data and computational resources. So we solved together last week a problem. The data set was small, but usually you will see that, okay, the ImageNet that we are talking, and there are millions of images, the networks that we have, for example, today I will introduce some, we usually train with whole millions of images, not thousands, hundreds. Our network, deep neural network, will be trained with millions of images, labeled images. So if you want to do this from scratch every time, for the problem that you have, it is computationally expensive and requires lots of time. So based on this fact, we can say that transfer learning is a type of learning strategy that transfers knowledge of learned model to new model. So we already have some model that we trained it based on some data set. Now we want to say, okay, let's transfer this knowledge to other network. Something like what human does, like we teach each other, we teach our children, we give the knowledge to our children so that they don't need to learn from scratch. So it's kind of similar, but we will see how in detail we can do that. So basically we can say model can be trained on one and reused in the other one as a starting point, for example. Instead of learning from zero, we can set it as a starting point of our second task or new model. So the main goal is clear. I explained that is to use the knowledge, but this knowledge in new network can be include features, patterns, or models, or whatever we can transfer from our existing model to new model. After doing that, then we want to improve the performance or speed up the learning rate of new model and on the other tasks that we have. So always we have two tasks. We already learned some network, trained some network on task A. For task B, we want to use the knowledge by transferring some information from first learned network that we have. So now let's answer why. First, we want to answer why and when to use transfer learning. If we want to first answer when to use transfer learning, first of all, we should consider that if our task is similar or not. If our task is similar, we say, okay, your target task is similar to the some tasks that has a model that we already learned. So this allows you to influence data, influence the learning on new network that you have to retrain the task. So as the name is very simple, we can consider that in similar tasks we can use it. Second item that we can use transfer learning, we can consider when you don't have enough data to train your model. So what does it mean? It means that you have millions of data, you train one network, but in new tasks you have 100, 500, 1,000 of data. Now that 1,000 of data, of course, maybe is not enough for your problem for deep learning task. But since you already have a network that learns based on millions of data, now what if you use that knowledge in order to only train your 1,000 samples that you have, hoping that your new network that learned this new data can use the previous information and get generalized based on kind of understanding both those together. So if we want to say when to use transfer learning, a second one, we can say when you have limited data. Another limitations can be what? The computational resource. If you want to use, if you want to train millions of data on your network, of course this takes weeks on very strong GPUs, for example. So that's very costly. And let's say you know all the parameters, hyperparameters, fine-tuning, and one shot you want to train it, but it takes weeks. So that's not feasible sometimes. Even maybe you don't have that strong GPUs to train it. You don't have access. So that we can then also use transfer learning. So it's clear that it will be able to reduce the need for training for our model, and that's kind of interesting point that we want to have. Now if we want to say, okay, if we answered when, but if we want to answer why use transfer learning, I think it should be very clear for you. First of all, improving performance. Transfer learning can have better model performance generally. When you converge your model, at the end of convergence, you see that it converges not only faster, but also most likely converges better. Especially if you have limited data for new tasks, this can be visible much more. Second one, efficiency. We can save computational resources, time, with using the existing model that should be very clear as I explained. Besides, we can mention that we can avoid overfitting. How we can avoid overfitting? Think a little bit about it yourself. This transfer learning and transferring the knowledge. So obviously, in second task, if you have less amount of data, whatever you do, your network most likely is going to overfit. Because your amount of data is small, quickly your network can train based on the whole data that you have. Memorize everything. Like if I write two numbers here for you, 2, 5, you can quickly memorize, right? 6, you can still quickly memorize. But I fill the numbers, fill the table, fill the whiteboard with the numbers, you cannot memorize. So that's the same. If you have less amount of data, your network quickly look at the data and says, okay, overfit. So now we can say, okay, if you try to use transfer learning and say, okay, I don't want to have a pure network to look at the data and memorize. I want to use a pre-trained model that already knows many things, but I also want to add this to the knowledge of that pre-trained network. So that is how also we can consider that it's avoiding overfitting problem for our task. So now let's talk about different types of transfer learning. We have generally 3 different types. We can say they are usually categorized by the relationship between the source and target task. So how their source and target task is related to each other, we usually categorize based on that. That the concept is pretty simple. First of all, we say we have inductive transfer learning. In inductive transfer learning, the source and target are different, but they share same input space or domain of data. So source and target tasks are different, but they share same input. So we have an example. Let's say you have a problem of the classification and a problem of prediction or regression that you clearly know now. Okay, now we can say if you want to solve, you have 2 tasks. Task A already we have some knowledge. Task B we don't have. One of them is classification, other one is regression problem, right? So totally different problem that we solve. But the input is the same, some visual image that are coming. So if you want to use transfer learning in this stage for this problem, we call it as inductive transfer learning. Second category is called transductive transfer learning, so that here we say both source and target tasks are the same this time, but the domains are different. Kind of vice versa of the first one. For example, you can consider both of them are classification, but for example, you have different kinds of visual images. Different kinds of visual images can be image from different perspectives, different cameras, different environments, or can be like even different visual information. 3D mesh point cloud is one, another one is the RGB image, for example. So this is called transductive transfer learning. One point that I didn't mention to you guys, you can still use deep learning for 3D mesh cloud, and from LiDAR scanner you can scan the environment, that it still can go to the deep learning model that you have, you can train something to extract over there too. For example, classification task that we used, trained last week, you can give 3D mesh point cloud as input and train the same model, and it will classify the data for you. So I did some project based on that too, and works pretty fine. And as third class, we say we have unsupervised transfer learning. In unsupervised transfer learning, in transfer learning field, we say both source and target tasks are unsupervised learning, and they are totally different. So we can say, okay, we have classification and regression tasks, for example, and on the other hand, the data is also totally different. So of course, it's obvious that this is the hardest one to achieve. If we want to break it down a little bit, for example, inductive transfer learning, let's see, as we said, we say learn a source task, use the knowledge to improve the learning of the target task. First, task A and task B. So as example, we can say for source task, we want to train a network model to recognize various types of animals in one image. So it's kind of classification task. You can say this is cat, this is dog, this is elephant, this is a zebra, etc. So what will happen in the first task that we have, we say our model will learn to identify the features, patterns, and important items for recognizing the animals. We saw how we can do that. We define convolutional neural network, and we say that convolutional layers can abstract the features, can learn low-level features in order to add some layers. At the end, we end up with fully connected layer to classify. We understand this last week completely, that how features are coming, how patterns are coming, and we can train the model based on that. Now, let's say we have this already, the course from last week, the implementation. Now, if we want to define a new target task, here also, for example, we can say the colors, the shape, the textures will be extracted, of course. The texture, the shape is clear. For the colors, we can say if we use RGB, our model also learns the color concepts too. If we transfer it to grayscale, then we say color is not important, leave it, then it still will be shape, texture, and for example, edges. Now, after having this source task, if we say that now we have a target task, the target task, for example, can be an example of recognizing different breeds of dogs. Now you can think about it. Okay, I give you a problem and I say, okay, go train a model to recognize different breeds of dogs. You can go and train your model from zero, but we can instead use transfer learning and use the model that we already trained for animals, and already it extracted the features, patterns, the colors, shapes, and texture of all features from animals. And we maybe think that that can be useful for our target task. So that we can call it, instead of training a new model from scratch, we can use those trained model as a starting point of my new problem that I have. So any question? Is it clear? The concept is quite simple. So we say here, okay, this model already has useful information that we can use it in our model. Now, if you want to open it up, the relationship between deep learning and transfer learning, there are some predefined and well-known concepts. First of all, we call it as synergy. In synergy, we have in this specific relationship, we say deep learning and transfer learning work well together. Deep learning model can learn hierarchical, abstract representation of data, which are often useful for many tasks. The second relationship can be pre-trained models. Deep learning models, for example, VGG, BERT for text, VGG usually used for image. I will introduce BERT for text classification and different things that we can do for the text. We already have very big networks with millions of data that they already trained, and they already captures the useful features, and they are available for us so that we can use it as a relationship between deep learning and transfer learning, so that, as I mentioned, these models can be starting point of our model that we have. Another element is feature extraction. Again, should be very clear that higher level representation in deep learning model can be used as pre-trained model to transfer for new model. What does it mean? It means that, for example, we will see different models, but you have multi-layer deep learning model. At the first layers, you have, for example, convolutional layers. These convolutional layers learn to extract features from image, the voice, the text. So these first layers are quite useful as feature extraction to be transferred to other models instead of, again, doing that separate. And another relationship between deep learning and transfer learning is simple fine-tuning, so that we say in this method we continue training, for example, updating the weights of the network that we have in new model. Now let's have a look at one of the well-known deep learning models. Most likely you've seen it already, but let's have a look how does it look like. First of all, we want to talk about visual geometry group, VGG. It's from University of Oxford for image classification. It has a simple and very uniform structure, simple to understand. And the main contribution of the VGG network can be listed as showing the concept that if we add more depth to network, it's useful. Before VGG, the researchers were believing that most likely adding more depth to the network is not very useful. The parameters, number of the neurons, and those are more important. But VGG shown the community that, okay, if we add more depth to the network, it can be pretty useful to catch the concept from the image and the problem that we have. I'm exemplifying image, but of course you've seen many tasks. So for VGG we have different versions depending on number of layers that we have. For example, VGG 16, VGG 19 are two common ones that we can mention it. And you can have a look at the VGG 16's structure. We have the input, and whole whatever is inside you already studied, you know it. We have, for example, two convolutional layers, convolution 1, 2, then one max pooling layer. Then again 2 convolution, 1 max pooling. Again 3 convolutions, then max pooling. 3 convolutions, max pooling, 3 convolution, max pooling, and 3 layers of dense at the end. So based on last week's course, even you can create the model yourself by adding these layers all together and train based on the data that you want to do. But of course, if you use libraries, if you use PyTorch, this is very simple. What we can do, instead of whole implementations that we did, we can write one line. all the lines of code that we develop our model, you can write simply VGG model or the name that you want as variable equal to models.vgg16. Already implemented for you guys. Just then you can train it. Just load the model and train in one very small line. So the second model that I want to quickly introduce is a residual network, neural network, ResNet. Is also another very common and popular, famous one. Of course, recently we have much more advanced networks. I showed you the website and where you can check it. But we want to now look at the base models for now. The ResNet is was like kind of highly influential on the field of deep learning, and the reason was that ResNet was the winner of the ImageNet competition in 2015, and it got trained with 1.2 million images over there. So some research institutions, some researchers like you guys, there are some competitions, as I told you, on, for example, Kaggle, ImageNet, that still, if you can go and check. There are some available competitions even now. Every month there are competitions. So somebody said, okay, let me define this network. Think about the network structure, how layers should be, how dropout, how connections should be, different configuration, and the performance that he achieved beat everybody else. And because of that, this model became very popular and famous. What was the key innovation here? It was introducing skip connections. With ResNet, we introduced skip connections, and I will now explain how is it generally. So we also have different models. For example, ResNet 18, 34, 50, 101, 152, and represents how big. Oh. Okay, thank you. Hope it works. Yeah, it works. Okay, that's what's good, that now you're not sleepy anymore. I see all the faces. I sometimes maybe should throw it by purpose. Good. So we have different models of ResNet that just shows the depth of the network, simply the size of network and how it is big. How it looked like, if you look at the network structure, we have input-output. From input, we have zero padding basically in the predefined network. We have convolution layer. You know exactly what is it now. We have batch normalization. You know exactly what is it now. We have ReLU. You know exactly what is it now. We have max pooling. You know exactly again what is it. Then after this stage 1, there is stage 2. We have a convolutional block, one convolution layer, again pretty similar to what we have, just some differences. The only point that we don't know about this, and this is the innovation of this network, is ID block. That this ID block helps to deal with gradient vanishing problem that we studied. And we said that we have gradient vanishing problem when our network is deep, the input comes, we apply some weights deductions in different layers so that gradient is vanishing at the end layers. The weights that we want that shows the differences is already vanished. So because of that, I also introduced one approach to do that. We had different approaches. One of the approaches was to skip the connections. We said that input directly, whatever value comes, sometimes you pass it to the next layer. You don't reduce it. You don't map it to a smaller part, whatever it is. So when you do that, you skip the weights to flow into the network to the next layers. That then gradient vanishing problem goes away. Then you can use a larger network. Then your model learns better based on the data that you have. I put some notes here for you, the same explanations. we have identity blocks, that shortcut connections that allows the network to learn residual mapping much more easily. It means that we want to do that. With identity blocks, we help to solve the gradient vanishing problem by skipping connections and pushing forward the values that we have purely without mapping them to lower dimension. Okay, so any question? All right. So keep these two networks in your mind. What we do now, I will show you in the implementations and examples that, okay, the network that we define, deep learning model that we define together, based on the same implementations, we can redefine the well-known networks ourselves or use the library, one line of code I will show you to train it. But our focus today is not that purely. Our focus today is to see how we can use transfer learning. Is there any way that, for example, ResNet already trained based on ImageNet? Can I use that weight somehow to train my new model? We want to focus to see today more in details. So if we want to talk about one example of image classification, as I mentioned a couple of times, we can use a pre-trained VGG ResNet, which train with large set of images like ImageNet, and the extracted features can be used in new model, and often, most of the time, leads to have better performance and than if you want to train from scratch with random weights, with random network that you have, if we consider the approach that we want to transfer only the weights. And how we can do that, if you want to use again library, first of all, let me explain to you that this models.vgg 16, you can replace it with any model, well-known model that we have. Most of them are implemented in PyTorch, for example, or different libraries. You just replace the name of model that you want to train your model with. Then here we have a parameter that if we make pre-trained equal to true, for example, with VGG, what happens? This already implemented that we can use transfer learning. How? The VGG already trained by ImageNet. Even VGG 16 has been trained with 1.2 million images for you. And if you write pre-train equal to true, then your PyTorch library is going to, if you run it for first time, you will see that it's going to download something. And it's downloading the weights of network for you from pre-trained VGG image that we have. Then after training, your network's weight will not be randomly initialized this time. It will be initialized, but already a trained image dataset that you have. So that whatever you train, if you do this, will be continuation of the fine-tuning or adjusting the weights based on the weights that already trained over. You just need to simply write pre-train equal to true over there. I will show you again this in the code. So we discussed different benefits, but what are the challenges if you want to use transfer learning? First of all, we say it's not always beneficial. For instance, when the source and target task are not related to each other completely. So this is called negative transfer. If you use negative transfer, even you may get in trouble, and your performance will be even worse than random, because the weights are fine-tuned to some values, but if it was random, more likely your training speed and iteration would be nicer. So you should make sure that there are some meaningful connections between target and new task that you have, the source task. One point that it doesn't mean that you cannot transfer the weights from, for example, image classification to voice recognition. It doesn't mean that you cannot do. You still can transfer weights from image recognition problem to voice recognition. How this can be useful, you can think about it. For example, let's say we are training a model that we want to distinguish different animals based on their voice and based on the visual information. Finally, we want to extract some features to say this is elephant, this is lion, this is something else, right? So experiments shows that still it is useful to use transfer learning, even the things are, the input data are quite different from each other too. This is one point that worth to mention. It doesn't mean that you cannot use, okay, between different kinds of data. But on the other hand, one more challenge, sometimes differences between source and target domain can lead to have more challenge in the transferring the knowledge because of the difficulties that it can cause for you. Okay, now we need to know one more thing that is usually very important to be used in conjunction with transfer learning, and that's self-supervised learning. Let's define it. After definition self-supervised learning, you will see that, okay, why it's important. What is the definition? We say, okay, self-supervised learning is subfield of machine learning, that there the model learns to predict the part of missing data. So you have data, you want to detect part of missing data. In self-supervised learning, idea comes from the designing of the task where the labels or answers come from input data itself. Can you say any example for this? For this line? You can answer too. No, data set example, not algorithm. What kind of data can we have that answers come from input data itself? There are many. No idea? What data set?
The data set where you input as the image and output as the depth map.
Depth map? Don't think too complicated.
Yeah.
Think simple. Say it again. Can be too, but that's also another complicated thing. So let's say you have a lot of text, right? Then your algorithm, your self-supervised learning, removes some part itself, then tries to predict what was it. Very simple. You have one image. You hide some part, your algorithm hides some part, and tries to say, oh, well, okay, what was that? This is called self-supervised learning. Very interesting. But there are some reasons that I'm introducing it here. For instance, we say, okay, same thing, part of image or part of text. Our model can remove it and try to guess it. Let's say you have image, you hide this part, and your training model wants to say, okay, what was there? And can it guess if it was leg? So this is called self-supervised learning. Now you can think, okay, why this is important in transfer learning? How we can connect it to transfer learning? We should go buy breakfast and bring for you guys. If you have a small data set, is one very important thing. We said that in transfer learning, the motivation is that if you have a small data set, we want to use the big trained one to use it a small data set. Okay? Maybe we have label there, but if we don't have label, and if we have label for that, that's not problem. But if we don't have label and we don't want to have label there, so what we can do, we can use self-supervised learning. Why? Because, for example, in text classification problem or text semantic interpretation problem, we have billions of text. Can somebody label it? It's very difficult, right? So that's very common to use it in conjunction to with transfer learning, so that it's very common. Also, why it's very common, like ChatGPT that you guys are very interested in and using. This ChatGPT also is using both together, transfer learning that today we discussed and self-supervised learning together to train. ChatGPT 3 and ChatGPT 4 both are doing the same. I think I put some point over here too. Anyway, so one more point before I forget later to explain to you. So we learned supervised learning, unsupervised learning, reinforcement learning, we know. And now we discussed about self-supervised learning, and I said we have semi-supervised learning too. So since we know all, let's discuss about a semi-supervised learning too. In semi-supervised learning, we say, okay, we want to use both benefits of supervised and unsupervised. It means that I have some data that are labeled, but some of them are not labeled. If our algorithm can use both these together, we call it semi-supervised learning. That's very simple definition for that. So that you know all the classes of the machine learning techniques, including self and semi-supervised learning. All right. Now let's talk about recent advances of the transfer learning. First of all, in natural language processing, or NLP, we say that, as I mentioned to you, transfer learning revolutionized the NLP, and usually we use, they have used both of the self-supervised learning and transfer learning together to achieve the performance that nowadays they have. Of course, if they want to not use transfer learning every time and every new data that is coming, every new model that they want to train, you can imagine how hard it is, months of training on a very large data set and very costly. For example, GPT-3, 4, and Roberta, that is version of BERT that I mentioned to you, is advanced version of BERT for text segmentation and interpretation tasks are from Facebook are common to be used. So these models first are pre-trained based on massive corpus. Corpus is common in NLP term, that is indicating large connection of the texts that we have. It can be many documents or whatever, we call it as corpus. That they already learned the general structure and the semantics of the language that we can use. Also, we are not limited on one language in NLP. If you learn, for example, the concept in English, the Spanish language, the maybe Chinese language, maybe all the other languages have something similar concepts. So that the main general same concepts can be also used in transfer learning to use it between different languages. They are fine. Then you can fine tune for a specific task. For example, question answering. If you train on the text on the corpus by NLP, then you can use it for answering the questions, sentiment analysis, translation, and all other things that you may need. And usually they show state-of-the-art performance because we already trained the concept by the NLP, and now we want to do different tasks so that we can use transfer learning based on that to solve the problem. What about computer vision? Models like ResNet, VGG initially trained with large data sets. As we mentioned already, we can use it over there. Then you can often fine-tune the specific network based on, for example, for new task, object detection, image segmentation, medical image analysis, or whatever you need. For example, here, since you train the computer vision task with large data set, then you have new problem. For example, object detection, you have segmentation problem or medical image analysis problem, so that when your network already learned the feature extraction, what are the important elements over there, then you can change the task and you can achieve higher performance, faster performance results over there. On the other hand, we can have it on cross-model transfer. In cross-model transfer, we want to transfer the knowledge between different types of data. This is called cross-model transfer. For example, in computer vision, we can say pre-trained model from computer vision can be used for generated text description. So your machine learning model looks at the image and writes. So here, for example, if you take image from me, here professor is teaching. Here students are listening. There is a chair that is in front of table. So we have very common application that called image captioning, that machine learning model tries to describe whatever it sees in image by text. So in computer vision, we can transfer between these model as cross model transfer, and we can use it as I also mentioned, based on the visual speech recognition, that pre-trained model for audio speech recognition, also known as ASR, and visual lips movement together in order to predict something. It means that your first pre-trained model recognize voice. Second one, you want to train something detect from lips movement, so that transfer learning also shown very good performance if you transfer from voice to image and lips movement, so that it can say finally the objective is to detect some specific words. I say okay. So from voice, whatever your network has learned, the weights that your network has learned there can be transferred to the voice over there and shows good performance. On the other hand, we can use transfer learning not only in computer vision, also we can use it in deep reinforcement learning. So many of you, I know you studied the course with me last semester. Next semester also we will have it if you haven't. So in deep reinforcement learning, we can say we can transfer information from different environments and between different agents. What does it mean? Before discussing what happens, we say it speeds up the training process and better overall performance on training new agents. What we can transfer between agents in deep reinforcement learning, we can transfer the parameters. Parameters means the weight of the network, as I exemplified many times. Like you have trained one network for agent A, for agent B you can transfer the same weights and the parameters, and those can be good initialization for network instead of having random initialization. The second interesting transfer learning stage that we can do is policy transfer. What was the policy? Policy was indicating what your robot or agent is doing. For example, I'm standing here. If I move forward, if I move right, although these are actions, but these can be policy based on the environment. Policy means that I'm looking at the environment, making a decision, go right, this is my policy. Go right, this is my policy. So we can transfer the policy between agents. So, and this can be between different agents. What, for example, you trained one drone, the flying robot, to do something in the environment. The same policy that you have there, you can transfer it to mobile robot that moves on the environment. You may say, okay, those are totally different. Going right, going left in drone is totally different than agent that is moving on the ground. Yes, those are different, but usually they boost the training. At least you have some initial policy that is not doing totally stupid actions. Or totally random actions. You let your network to use other agents' policy as initial policy, so that hoping it can work good. But of course, if the robots are similar, that can be where you have industrial arm type A that needs to do something, you have some policy there, whatever task is. If you move the policy to other robot with other tasks, still those policy can be helpful to boost training and facilitate to find better answers at the end, even with policy transfer. So can we use two together? Of course, you can use two together. Parameter transfer, policy transfer. And if you want to continue knowledge distillation, that it means that we want to transfer knowledge from complex reinforcement learning agent to simpler agent. The complex one here, for the example, we have like somebody is teaching you something very complex and you want to quickly mimic it and abstract it and exactly say the same thing. Like I'm teaching you to do some complex procedure of a machine, then you watch it and do it in simple way. So that this is called knowledge distillation. You make simpler form of transferring the knowledge to the next agent over there. We say this can be done by moving, how practically, your question may be in reinforcement learning, how practically we can do that. Practically, you can move the experience reply buffer or part of experience reply buffer to new agent. What does it mean? Like, it means that you train agent A and it learned to do some actions and learned best optimal policy in the environment that you have. Then we say, okay, what was the last experience or reply buffer that it had? I want to copy it to my new agent. And my all calculations comes from there. So this is one practical way. Or you can bring the value function. If you remember, or if you're interested in, you don't know, I don't want to explain it. It's a long history. You can bring the value function. Or you can create heuristics or rules. Heuristic or rule is that my agent moving toward this obstacle. But I know for sure this is the obstacle and my agent cannot pass it. I can write heuristic. I can write if there is obstacle, don't go, don't try it. That's it. So that's called heuristic. This heuristic, for this example, I can do it myself, but heuristic can come from my previous agent. You can write some code that generates heuristic, some rules based on experience of previous agents, so that you can bring it to new agent and say that previous agent didn't try this, you don't need to try it too. Because that was optimum solution, then you just run this heuristic while you're learning your new task. This is very advanced topic. Also another advanced topic that we have with transfer learning in combination over here as multitask learning. With multitask learning, we want to learn multiple tasks together at the same time by one network. So not only, for example, image classification, you want to do also interpretation at the same time. For example, 2 tasks together or 3, 4 tasks together. It is called multitask learning in transfer learning. What we can do there with reinforcement learning, we can share representations or policies among the tasks real-timely. Here we do it offline, here we do it online. At the same time we share the information between them. If you search about multitask learning, you're gonna see many research articles, recent papers that they work multitask learning with, for example, deep reinforcement learning combination and use transfer learning to solve problems. And the problems that are complex and researchers are solving nowadays usually are engaging these all together. Now we have a question, can we apply transfer learning if network structure is different? If you want to move the weights of the network A to network B, suppose to the structures of network be same. Can you transfer it if they are different? Can you use transfer learning if they are different? What do you think? No idea? Okay, now you need lunch too, not only breakfast. The answer is yes. Transfer learning still is possible, but you need to find a way to adjust the network weight somehow to new network. You need to write some code. Because the value is too high, you say, although my network is different, my, for example, convolution layer is smaller than what I already have. The size is different, but I still want to bring it somehow. Then still, because kind of like, let's say you have image classification problem, although the convolution layer in original network is big, you want a smaller pawn, you may say, okay, somewhere in middle should be work also because we have image, pixels coming and something comes out. Again, here image comes out. Weights should be something similar, although my network is smaller. My layer size is smaller or bigger. You may say, okay, if it's bigger, I want to copy double it. Like copy first stage and rest stage, I want to fill it with the rest of the weights over there and try to see if it works. Basically, we have different approaches, formal approaches to do this. One is partial transfer. In partial transfer, we say early layers can be transferred. We say, okay, let's say we just want to transfer not whole network, some of the layers to new one only, not all of it. And other one is the feature extraction approach that we can use the pre-trained network with different structure as feature extractor, for example, only bring whole convolutional layer. And third one is model conversion that I explained. You can convert your weights and models to transfer between different networks. You can do all three or each one of these three if network structures are different between two models. So now, okay, we talked a lot how we can bring it to practice. It's simple. Simplest way, the most simplest way is to save the networks that you learned, you trained, and load it to new model that you have. How you can do that? Again, 2 lines of code. So in model A, let's say we didn't find it from internet, we have problem, we solved it, finally you save the weights. Of course, we don't use it only for transfer learning. If you want to train it, load it, and test it, you can use the same code. But here in transfer learning, you can write torch.save, the model state, dictionary and the path that you want to save. With this line, you can save the data in the directory that you want. Then next line, you can load it. And if you load it, and if you have new problem, you want to train it, you can use this line. For example, let's say last week I gave you one example. You train that model, you can add these two lines to save it. Today, another problem that you have, same code that I gave, same model that I gave you. Now you have new data set, new problem totally, then you can load it and use it. So that you have practice for that also for today. After I explain some code, you're supposed to continue giving example code that I will give you. For image classification, you need to apply transfer learning and demonstrate its effects on the problem. So you need to take very small data set so that it don't take long time and a small network. Train with some data set, and with data set B, then you're training with loading the weights. Without loading the weights, compare it to see if it learns faster or not. So this is the practice for today that you're supposed to do, and make sure that you're learning everything during. If I want to summarize what we discussed today, we understood transfer learning and why we should use it. We discussed different types of transfer learning, including the inductive, transductive, and unsupervised transfer learning. We saw deep learning model structures like VGG and ResNet, and also we understood that how we can say, okay, we can load the pre-trained data from internet in the code, and we can use transfer learning based on that. Then we introduced self-supervised learning, and we said that self-supervised learning can be used in conjunction of the transfer learning, and it's very advanced technique that can be used. It is nowadays our researchers and companies are using for example, in JackGPT 3.4 and different well-known models. And finally, that we discussed all the advances that we have.